So I'm going to present low-rank decomposition for frugal learning, so especially for compression and for growth of neural network. So, okay, compression is going from big neural network to small neural network, and growth is doing the converse, so it's logical to see them in a similar way. But this is a bit simplified because in practice, what we have is that compression is going to already train neural network to a small trained neural network, and growth is in general going from a seed architecture, so not trained, to a fully expected and trained neural network. So it's not exactly the same. Okay, so first I will present the case of fully connected layers. So that was what Guillaume presented. And then a convolutional layer that is a way to connect layers with convolution. We'll recall what it is. So first, fully connected layers. So imagine we have a network with a function that is computing things, then we have a x, and then we apply a linear layer, get a y, and then compute other things. The goal here is to get this layer and transform it to a smaller layer. So yes, to recall the expression, this means that y is equal to wx, where w is the parameters. So for example, if we can decompose w as a product BA, what we get is that our linear layer is approximated by two linear layers. So we can replace in our network LW by LA and then LB. And this gives us a new network that is an approximation of the previous one. So do we gain something with doing this replacement? And the question is, the answer is, it depends on the rank of the decomposition. So at the beginning, we have a full matrix that is of size, let's say, m times p. And computing wx requires mp multiplications. And computing b, and so computing the BAX through two layers require k times m plus p multiplication. So in the end, we have an improvement if the row rank is small enough. And in practice, as we often have very, very big neural networks, there is good reason to think that we can't find such a rank that gives us less operation after compression. So the question is, how do we choose A and B to approximate W? A simple way to do it is to solve this low-rank approximation problem. And this could be a good idea, and it's often what is done in practice. But if we look at a typical example of input, you can see that all pixels, so all input values, are not as relevant. For example, on MNIST, the value in the corner are typically always zeros. So basically, we don't care less about them. And so in a way, the solution what we had is well suited for isotropic input data. Because for anisotropic input data, all the values doesn't have the same importance. So to reflect this, we can have a data-dependent solution where what we care instead of approximating W is to approximating the output of the layer parameterized by W. So the output is Wx, and we approximate it by BAX. And we approximate it for X that is following the input distribution. So it's an expectancy about on the input distribution. So as almost always in machine learning, we approximate the expectancy by a sum. And what we can do is transform the sum in so we have here the sum, and we also can have a matrix writing. which is basically the same. And if you remember the previous presentation, this is the problem of adding neurons. Because if we have the first layer here with where we have a value, here a second layer, and here a third layer, we have here an input x, and we can have a gradient of the activity. So let's say, for example, if we have y, we can have the derivative of the loss according to y. So basically, if we add layers here, neurons here, but it is like adding a first layer parameterized by A and a second layer parameterized by B. And so what we want is to go in the direction of the gradient. So we want to minimize the difference between the direction of the gradient. Okay, we want to do a gradient descent, so let's put a minus sign. And what we add, which is BAX. And if this is y in the case of linear regression. So you see that we have here the same problem as for growing. When for compression, we remove intermediate neurons in some sense. And here we add neurons. Okay. So now, yes. So in the case of growth, we suppose that there is an activation here, but we do a first order approximation, and we approximate it by sigma prime of 0, and we choose in general that it's equal to 1. So it's true for many activation function, and otherwise it's just a coefficient that can be handled. And this is okay as an approximation because we can suppose that the weights in A are small, so the input will be close to 0. Okay. So maybe another point of view on the problem that leads to the same minimization problem. If we look at this way, this could be seen as a linear regression with a sort of regularization that is that our weight matrix is low rank. So this could be compared somehow to a lasso linear regression or bridge regression, but here with a different regularization that has different properties. And if we put y equal x, we have here the principal component analysis problem. So the goal is to find a subspace that approximates at best or data, and with a linear transformation. And so if we replace x again by y, we could see this as a sort of supervised PCA, as the latent space of small dimension is dependent of the output data and not only on the input data. Okay, so how do we solve this problem? The first idea is to first compute the full rank solution and have W star, and then approximate the full rank solution with a low rank matrix. And here the result won't be necessarily the same, and it's for the same reason as we used a data-dependent norm in the case of neural network compression. It's because all the directions are not equivalent, and all the direction doesn't have the same importance. So to solve this, we can use the covariance norm, or as semi-norm. So we have input data X, and we define the covariance of X, and we have a quadratic form associated and a norm. And we have the following theorem that says that O minimization problem is equal to the distance between O solution and the optimal full rank solution plus some constant. So we see that optimizing this according to W is like optimizing this according to W. And here it's not a Frobenius norm, it's a norm that is definable. So we have the following scheme where we just replace here the low rank approximation by a low rank approximation according to the norm S. And we can solve this efficiently because we can compute the covariance norm with the Frobenius norm, just multiplying inside by a sort of square root of our covariance matrix. And then we have this problem that is transformed in a Frobenius approximation. And finally, by doing a change of variables, we can get back to a classical low rank approximation that can be solved thanks to the Eckart-Jung-Mirsky theorem by SVD. So we have a closed form solution that is quite efficient to compute in practice. S is a covariance of the data. So X transpose X. Oh, yeah. And so there is another solution to this problem that involves different computation, and in particular that involves the SVD of the input data X directly. And we chose to avoid this because in our case we could have a lot of data, and so we could compute the covariance matrix and then do SVD on a small matrix. In practice, it's more efficient. So now for convolution layers. So what is a convolution layer? So if we have an input images, so with of height h and size w, and you have a certain amount of channels. You can see channels are sort of colors. For example, RGB images are 3 channels, R, G, and B. But in the case of neural network, in general, we add channels that can represent something more than colors. The different type of information, and it's up to the network to learn what it put inside. And the convolution is parameterized. So for one output channel, we have a block that is of size of the part of the image, and that we slide the block along the image, and for each position of the block, we have an output pixel that is the result of multiplication of each value in the block by each value covered by the block in the image. And then we have a certain amount of output channel T, and for each output channel, we have a different block, so a different set of parameters. So in total, parameters is a 4th order tensor, because we have 1 order for the number of input channel, 1 order for the number of output channel, and 2 order for the size of the image. So in general, for the convolution mask in general, we can talk about the convolution mask also. So we'll do the same as for linear layers, but here, instead of having a linear layer, we suppose we have a convolution. So we have a convolution kernel K in this size, so HGWD is the size in the space size, and again, we approximate for kernel K by a series of products of smaller tensor or smaller matrix, and we could replace the convolution by a series of layers. Okay, here I don't precise how they are multiplied and which layer it is, because it depends of the convolution of the decomposition we choose. So, for example, we can start with maybe the most famous decomposition for tensors, which is the CP decomposition. And the idea is to approximate that. In the case of matrix, we approximate by the sum of product of rank 1 matrices that are vectors multiplied by value, singular value. And here it's the same, but instead of having only 2 vectors, we have as many vectors as there is orders. So for example, here we have order 3, so we have 1, 2, and 3. And then if we have a matrix, a decomposition of rank 3, we have 3 different sums, different terms in your sum. And so here, if we have at the end where we have an input tensor of size ABC, at the end we have only R times A plus B plus C parameters. So again, if the rank is small enough, we have compression. Okay, but here it's less trivial than in the case of linear layers to replace a convolution by a series of sublayers according to this decomposition, but it can be done. So here we have our tensor that parameterizes our convolution. So you see the 4 orders, and here there is the CP decomposition. Thus, I just stack each singular vector together. So we have all the singular vectors for the dimension, so for the order T, all the singular vectors for the order S, etc. And so what we will have is that the first order S will give us linear operation, but considering each different pixel as a different input. Give us the first layer. Then the decomposition over the order that corresponds to the space will give us a vertical convolution, so only doing with some convolution with 1 vector instead of having a full block. And then we have also a horizontal convolution, and then again a linear layer in the depth to reconstruct a full size output to have T. So this is a way to decompose our tensor and then to replace our convolution layer by a series of smaller layers that will be cheaper to compute. Another way to do it is a Tucker convolution decomposition. So it's basically the same idea, but instead of having 1 singular value per rank, we have here different rank, and for each possible product of singular vectors, we have a different singular value. So here we have a sum over all the different possible product of singular vector. For example, the first one of the order 1, let's say the third one of the order 2, and the 5th one of the order 3. So it's a possible combination. And there is a singular value associated. So it's a different generalization of the SVD. So because if you look, CP and Tucker will give the same in order 2. And so again, we can replace 1 convolution by a series of layers. So here instead we choose not to decompose along the size of the kernel. And what we get is that we have first, again, linear operation on the depth. And then we have a full convolution, but of smaller size, because we have less channels here. The number of channels is lower. And then again, a fully connected layer of linear operation to reconstruct the output. And here that we can see in the 2 examples is that we never got transform a convolution in a series of 2 convolutions. And this is what we would have in the case of growing convolution layers. Because in the case of growing, what we have is a first convolution here, a second convolution here, and we want to add a certain amount of intermediate channel. And so to have here a larger convolution and here a larger convolution. So we will have a way to decompose a convolution into two small, two convolutions with a small intermediate number of channels. And so in the case of growth, the problem is different. So we have this problem to solve. So we have a target y, an input x, and we want to transform first with a convolution A, then with convolution B. And this is, we want to transform it in a linear problem. And so there is multiple solutions, use Toeplitz matrix, it's like repeating the parameters, or using to repeat and reshape the input to make it linear. And with those tricks, we achieve to express it as a series of tensor and matrix operation. But unfortunately, it's still not enough to solve it, so I will just skip on the technical thing. And we had to have a relaxation of problem. So here, a simpler way to see the relaxation is to see that minimizing this is like maximizing the scalar product under the constraint that the norm is less or equal to 1. So it's equivalent up to a scaling factor scaling the solution, but in our case, we are not interested by this scaling factor. And instead of minimizing having this constraint, we have a constraint that is a bit bigger, that is directly of the parameters, and we have that the parameters should be less or equal to 1, with a covariance matrix that takes into account only a part of the interaction in the input. So not all covariance, but only a part of the covariances. And with this relaxation, we are able to solve with the same technique as for linear layers, that is with an SVD that is closed form, so it's very efficient. So in conclusion, we saw that for fully connected, compressing a neural network or making it grow lead to the same optimization problem, that is a sort of low rank linear regression that can be solved efficiently in closed form. And for convolution, the problems are different. And depending on the decomposition, we could have different restructuration of our network. And for growing, we achieve only to find to solve a relaxation of our problem. And so future work would be to better characterize how good is this relaxation, and also maybe find an exact way that is not directly impossible. And if you find an exact way, this could be also applied to compression, way to decompose it. Okay, thank you for your attention. And if you have questions.